Show a vision language model a single picture with something dangerous in it, and modern safety training will usually catch it. But here's the unsettling part. Hand the model two perfectly innocent images, and the combination can ask for something harmful, and the model walks right into it. This paper is about that blind spot and a surprisingly elegant way to close it. Let's set the stage. Vision language models, VLMs, are now everywhere, and a lot of work has gone into making them safe. With a single image, that effort largely pays off. If a picture contains something unsafe, the model tends to recognize it and refuse. The single image case feels mostly solved. The real world isn't one image. People compare photos, flip through documents, send several pictures at once. And that opens a gap. Take a benign photo of a camera and a benign photo of a bedroom. Each is harmless. Together, with a neutral-sounding question, they can imply illegal surveillance. The danger lies in the relationship between the images, not in any one of them. So how bad is it? The authors test 14 strong vision language models, open and commercial, on multi-image safety. The result is brutal. Most open models get jailbroken on around 90% of cases. The attack success rate sits near the top of the scale. Even the best commercial systems fail roughly 40 to 65% of the time. Multi-image safety is basically wide open. The obvious move is to fine-tune for safety. But existing methods break in two opposite ways. Some, like textual fine-tuning, become overcautious. They start refusing harmless requests, blurting out "I'm sorry" even when nothing is wrong. Others stay helpful, but never learn to catch the hard, reasoning-heavy cases. You sacrifice either safety or helpfulness. Paper's core diagnosis is what it calls a safety reasoning gap. These methods teach a model to memorize that certain inputs are unsafe, but not to reason about why. So when harm only emerges from combining what's in the images, the model has no path to figure it out. It never learned to look, reason, and then decide. They trace that gap to two concrete bottlenecks in how safety fine-tuning is built. First, the inputs. Training only ever shows single images, so the model never practices reasoning across multiple images. Second, the labels. The target answers are just blunt refusals, with no reasoning shown, so the model never learns the thought process. Fix both and the gap should close. Their answer to the first bottleneck is a new dataset called MIS, the first multi-image safety dataset. Each sample pairs a neutral text question with two images, and the harmful intent comes only from how those images relate. It spans 6 harm categories, with easy cases where one image is obviously unsafe, and hard cases where both images look completely innocent. Their answer to the second bottleneck is the clever part: safety chain of thought labels. Instead of teaching the model to just say no, each training answer walks through the reasoning. First, describe what's actually in each image, then reason about whether combining them is unsafe, and only then give a safe response. The model learns to think, not just to refuse. Building this dataset is itself a 4-step pipeline. First, large models extract unsafe elements from existing safety benchmarks. Second, those elements are turned into a harmful query, then carefully detoxified into a neutral-sounding question. Third, a text-to-image model generates and refines the two matching images. And fourth, human experts plus GPT-4o filter and classify everything into clean subsets. Train a model on this data, and you get their method, MIRage, short for multi-image reasoning safety. They fine-tune the open intern VL model on roughly 4,500 examples. And notably, only 11% are generic helpfulness samples, a third of what rival methods need, because the reasoning labels do the heavy lifting. Now the payoff. On the multi-image safety test, the base model's attack success rate sits around 80%. After MIRage, it drops to essentially 0. And look at the right side. The rate of giving safe answers through actual reasoning jumps from the low teens to nearly 100%. It's not just refusing more, it's reasoning more. And reasoning is exactly why it beats the alternatives. Textual fine-tuning chokes on hard cases with innocent-looking inputs. VLGuard does fine on easy cases, but stumbles when real visual reasoning is needed. On the genuinely challenging benchmarks, the ones that demand reasoning to spot the unsafe intent, MIRage consistently comes out on top. Here's a result that surprised even the authors. They stripped 2 whole harm categories, privacy and self-harm, out of training entirely. Then they test on exactly those unseen categories. Base model gets jailbroken around 60 to 70% of the time, but MIRage still drops it to near zero. The safety reasoning it learned transfers to risks it never saw. And crucially, none of this comes at the usual cost. Remember, safety fine-tuning normally makes models dumber or more prudish. MIRage doesn't. Across 5 general ability benchmarks, it actually edges out the original model, a gain of about 0.83% on average, while using the least extra helpfulness data. Safer and slightly smarter. The authors are honest about the edges. MIRage isn't bulletproof. It can still be cracked by some determined adversarial attacks. The harmful images are largely synthetic, and they note real-world photos behave a little differently. And they point to richer reasoning labels or reinforcement learning as the next step towards stronger safety reasoning. Why does this matter? Because as these models start handling several images at once, the dangerous cases won't be a single shocking picture. They'll be ordinary images that only become harmful in combination. This paper shows the right fix isn't more rigid refusals. It's teaching models to look carefully, reason about what they see, and then decide. Safety, it turns out, is a reasoning problem.